Welcome to my sleep science channel. Please like, subscribe, and tell me where you are watching from. Tonight, we begin a quiet journey into one of the strangest and most fascinating ideas humanity has ever discovered: quantum mechanics. Long before anyone spoke about wave functions or superposition, people understood the world through familiar experiences. A stone thrown into the air follows a predictable path. Rain falls downward. A clock ticks at a steady rhythm. The moon circles Earth. Everyday life appears calm, solid, and understandable. For centuries, scientists believed that if enough information about an object could be gathered, its future could be predicted with almost perfect certainty. The universe seemed to behave like an enormous machine, with every piece moving according to fixed rules. This view became especially powerful after the work of Isaac Newton. His laws of motion explained the movements of falling apples and orbiting planets with remarkable success. Engineers could design bridges. Sailors could navigate oceans. Astronomers could predict eclipses years in advance. The same mathematical rules appeared to govern everything from cannonballs to the motions of the planets. Classical physics seemed capable of explaining the entire universe. As the 19th century progressed, scientists developed increasingly precise instruments. Better telescopes, more accurate clocks, and improved methods of measurement revealed details that earlier generations could never have imagined. At first, these advances strengthened confidence in classical ideas, but eventually, tiny cracks began to appear. Certain observations simply refused to fit into the old picture. One mystery involved heat and light. Heated objects glow with specific colors depending on their temperature. A fireplace ember shines red, while hotter metal becomes orange, yellow, and eventually white. Physicists expected that classical equations should perfectly describe this process. Yet the predictions produced impossible results. The mathematics suggested that extremely hot objects should release unlimited amounts of energy at certain wavelengths. Nature clearly behaved differently. Another puzzle came from atoms. Ancient philosophers had imagined matter as being made of tiny building blocks. But by the late 19th century, scientists had accumulated evidence that atoms were real physical objects. The problem was that classical physics could not explain why atoms remained stable. According to traditional ideas, electrons moving around the nucleus should continuously lose energy and spiral inward. Matter itself should collapse. Yet the tables, mountains, oceans, and stars around us obviously existed in stable forms. Light created additional confusion. Sometimes it behaved like a wave, producing interference patterns similar to ripples spreading across a pond. Experiments strongly supported this wave picture, yet other observations hinted that light occasionally behaved more like tiny particles, carrying individual packets of energy. It was as if nature itself refused to choose a single identity. Scientists found themselves in an unusual position. The old theories worked beautifully for planets, machines, and everyday objects. But something entirely different seemed to govern the smallest scales of existence. The world beneath ordinary experience was beginning to reveal itself, and it appeared far stranger than anyone had anticipated. Imagine shrinking smaller and smaller, smaller than grains of sand, smaller than cells, smaller than molecules. Eventually, you would arrive at a realm where familiar concepts start losing their meaning. Objects no longer possess definite positions in the way that baseballs or cars do. Events become governed by probabilities rather than certainties. Matter behaves like waves, and waves sometimes resemble particles. Empty space itself is not truly empty. Reality becomes less like a collection of solid objects and more like a constantly changing tapestry of possibilities. None of these discoveries emerged because scientists wanted mystery. They emerged because careful experiments demanded new explanations. Quantum mechanics was not invented to make the universe seem strange. It was created because nature itself insisted upon it. The equations developed during the 20th century repeatedly matched experimental results with astonishing accuracy. Again and again, observations confirmed that the microscopic world follows rules very different from those governing ordinary human experience. Despite its unusual features, quantum mechanics quietly shapes almost every aspect of modern life. The atoms inside your body remain stable because of quantum principles. The light produced by stars depends on quantum processes. Lasers, computer chips, magnetic resonance imaging, and many technologies used every day rely on ideas that would have seemed impossible to earlier generations. Perhaps the most remarkable aspect of quantum mechanics is that it emerged from ordinary questions. Why do hot objects glow the way they do? Why are atoms stable? Why does light behave differently in different situations? Simple observations eventually opened the door to an entirely new understanding of reality. The journey began not with abstract philosophy, but with practical attempts to understand the things people could see, measure, and touch. As the 20th century approached, these mysteries were waiting patiently. The familiar certainty of classical physics had begun to fade, and beyond it stood a new landscape, one filled with probabilities, invisible waves, and discoveries that would forever change humanity's understanding of the universe. By the end of the 19th century, many physicists believed that most of nature had already been explained. The laws of motion developed by Isaac Newton had proven extraordinarily successful, and the equations describing electricity and magnetism had unified several seemingly unrelated phenomena. To many scientists, only a few small details remained unresolved. Those details, however, would soon open the door to an entirely new picture of reality. One of the puzzles involved something surprisingly ordinary: the glow produced by hot objects. A piece of iron placed into a furnace gradually changes color as its temperature rises. At first it becomes dark red, then orange, yellow, and eventually bright white. Everything around us emits electromagnetic radiation depending on its temperature. Human bodies, candles, stars, and even the walls of a room constantly release energy in this way. Physicists wanted to understand exactly how this process worked. To study the problem, researchers imagined a perfect object capable of absorbing all incoming radiation. Such an object became known as a blackbody. When heated, a blackbody emits radiation with a characteristic distribution that depends only on temperature. Experiments measured this pattern with remarkable accuracy. Yet classical physics failed completely when attempting to explain the observations. According to the accepted equations of the time, a hot object should produce enormous amounts of radiation at extremely short wavelengths. In fact, the calculations predicted something absurd: an infinite amount of energy. Since no real object possesses infinite energy, it was obvious that something fundamental was missing. This embarrassing contradiction became known as the ultraviolet catastrophe. Nature was clearly following rules that existing theories could not describe. In 1900, a German physicist named Max Planck approached the problem from an unusual direction. He was not trying to overturn physics or invent a revolutionary theory. His goal was simply to find a mathematical formula that matched experimental measurements. After considerable effort, Planck discovered an equation that reproduced the observed data perfectly. However, achieving this success required an assumption that seemed almost unbelievable. Planck proposed that energy could not be emitted or absorbed continuously. Instead, energy came in tiny discrete packets. These packets were proportional to frequency and depended on a new constant of nature, which would later become known as Planck's constant. Rather than flowing smoothly like water from a faucet, energy behaved more like individual drops falling one by one. At first, even Planck himself viewed this idea as little more than a mathematical trick. The concept contradicted centuries of scientific intuition and everyday experience. Quantities usually vary continuously. A dimmer switch can gradually brighten a room. A car can travel at many different speeds. Water can fill a glass to any level. Nature appeared smooth and continuous. Yet the equation suggested that, at microscopic scales, energy might be fundamentally granular. A few years later, another physicist recognized the deeper significance of Planck's proposal. Albert Einstein examined a phenomenon called the photoelectric effect. Experiments showed that shining light onto certain metals could eject electrons from their surfaces. The strange part was that increasing the brightness of light did not always increase the energy of the emitted electrons. Instead, the frequency of the light played the decisive role. Classical wave theory struggled to explain these results. If light were simply a continuous wave, then brighter light should deliver more energy regardless of its color. But experiments stubbornly disagreed. Einstein suggested a bold explanation. Perhaps light itself consisted of individual packets of energy. These packets, later called photons, carried specific amounts of energy, determined by their frequency. Blue light, with its higher frequency, contained photons carrying more energy than red light. If a photon possessed enough energy, it could free an electron from the metal surface. If not, no amount of increased brightness would compensate. The experiments fit Einstein's explanation beautifully. Light, long understood as a wave, suddenly seemed to possess particle-like properties as well. Many scientists initially resisted the idea. Waves and particles appeared to represent completely different categories. A wave spreads through space and can interfere with itself. A particle occupies a more localized position. Yet nature seemed unwilling to respect these distinctions. Light displayed characteristics of both. The implications extended far beyond glowing objects and metal surfaces. Planck's constant, an incredibly tiny number, revealed that the microscopic world operates according to rules hidden from ordinary experience. Because Planck's constant is so small, quantum effects remain invisible in everyday life. Baseballs, mountains, and oceans contain such enormous amounts of matter that their quantum behavior becomes effectively averaged out, producing the smooth reality humans normally observe. As experiments became increasingly precise, evidence supporting quantization continued to accumulate. Atoms emitted light at specific wavelengths rather than across continuous ranges. Chemical elements produced distinctive spectral fingerprints. These patterns hinted that electrons inside atoms occupied particular energy levels instead of moving freely through every possible state. The universe was beginning to reveal an unexpected structure. Beneath the familiar world of continuous motion and solid objects lay a hidden layer where energy arrived in tiny packets, where light behaved both like a wave and a collection of particles, and where long-established assumptions no longer held. Scientists had not yet discovered the full meaning of these clues, but the foundation had been laid. Without realizing it, Max Planck had opened a doorway into one of the deepest revolutions in human understanding. What began as an attempt to explain the glow of heated objects would eventually transform physics, chemistry, technology, and humanity's view of reality itself. The calm certainty of classical physics had encountered its first great challenge, and a strange new world was slowly emerging from the shadows. For centuries, scientists believed that the categories of nature were clear and separate. Particles were particles, and waves were waves. A grain of sand, a raindrop, or a cannonball represented the idea of a particle. Such objects occupied definite locations and traveled along specific paths. Waves, on the other hand, behaved very differently. Ripples spreading across a pond, sound moving through the air, and vibrations along a string were examples of waves. Waves extended over space, overlapped with one another, and produced interference patterns. These two concepts seemed completely distinct, and few people imagined that nature might blur the boundary between them. During the 19th century, evidence strongly supported the idea that light was a wave. Experiments showed that light could bend around obstacles, combine with itself, and create patterns of bright and dark regions through interference. Such behavior matched the properties of waves perfectly. James Clerk Maxwell's equations provided an elegant mathematical description of light as an electromagnetic wave traveling through space. To many physicists, the question seemed settled. Then came the work of Albert Einstein and the photoelectric effect. Light, despite its undeniable wave properties, appeared to arrive in tiny packets of energy called photons. Suddenly, the neat distinction between waves and particles began to dissolve. Light seemed to possess both identities at the same time. Depending on the experiment, it behaved like a wave or like a stream of particles. This was deeply unsettling. Human intuition preferred clear categories, but nature appeared indifferent to those preferences. Even more surprising discoveries soon followed. In 1924, a young French physicist named Louis de Broglie proposed an astonishing idea. If waves could sometimes act like particles, perhaps particles could also behave like waves. This suggestion seemed almost absurd. After all, matter appeared solid and localized. A baseball does not spread across a stadium like a water wave. A pebble thrown into a lake follows a definite path rather than interfering with itself. Yet de Broglie suggested that every particle possesses an associated wavelength. His idea implied that electrons, atoms, and even larger objects have wave-like properties. The wavelength becomes smaller as an object's momentum increases. For everyday objects, the wavelength is unimaginably tiny, far too small to observe. That is why cars, trees, and planets appear to obey classical rules. Their wave characteristics are effectively hidden, but for extremely small particles, these wave properties become impossible to ignore. At first, de Broglie's proposal seemed speculative. Then experiments provided remarkable confirmation. Scientists directed beams of electrons toward crystals and observed the resulting patterns. Instead of behaving like tiny billiard balls, the electrons produced interference effects identical to those expected from waves. The evidence was unmistakable. Electrons, which had long been regarded as particles, displayed wave-like behavior. Imagine throwing countless tiny marbles through two narrow openings and observing where they land. Ordinary particles would simply create two clusters corresponding to the positions of the openings. Waves, however, produce a more intricate pattern. Their crests and troughs interact, reinforcing one another in some regions while canceling each other in others. Astonishingly, electrons produced the wave pattern. They behaved as though each electron somehow explored multiple possibilities simultaneously. The implications were profound. Matter itself could no longer be described solely as collections of miniature solid objects. Instead, particles possessed characteristics associated with both waves and localized entities. Neither picture alone provided a complete description. Physicists gradually realized that familiar words like particle and wave were approximations, useful concepts that captured certain aspects of reality but failed to encompass the full truth. This strange dual nature helps explain why atoms are stable. If electrons behaved only as tiny particles orbiting a nucleus, classical physics predicted they should rapidly lose energy and collapse inward. But when their wave properties are considered, electrons occupy standing wave patterns around the nucleus. Much like vibrations on a guitar string can only exist at specific frequencies, electrons can only occupy certain allowed states. These quantum structures give matter its stability and determine the chemical behavior of every element. Wave-particle duality also shapes the world around us in countless ways. The colors emitted by atoms, the operation of lasers, the properties of semiconductors inside computers, and many features of chemistry depend upon this remarkable behavior. The very existence of solid matter arises from principles rooted in the wave nature of particles. Despite a century of study, Wave-particle duality remains one of the most fascinating aspects of quantum mechanics. Scientists have developed mathematical frameworks capable of predicting experimental outcomes with extraordinary precision, yet the underlying reality still challenges ordinary intuition. Are particles truly waves? Are waves somehow particles? Or are both descriptions merely imperfect attempts to describe something deeper that human language struggles to capture? Nature offers no simple answer. Instead, it presents a reality richer and stranger than the categories people once believed were absolute. At microscopic scales, certainty gives way to possibility, and familiar distinctions begin to blur. The universe reveals itself not as a collection of rigid labels, but as a subtle and interconnected system whose behavior often transcends everyday experience. What seems impossible from the perspective of ordinary life becomes natural in the quantum world. There, matter and energy follow rules unlike anything visible on human scales, and the line separating waves from particles becomes less a boundary and more a gentle transition within a deeper and more mysterious reality. Among all the experiments ever performed in physics, few have inspired as much wonder and confusion as the double-slit experiment. At first glance, the setup appears almost unbelievably simple. A source emits particles or light toward a barrier containing two narrow openings, and behind that barrier sits a screen capable of recording where the incoming objects arrive. Nothing about the arrangement seems extraordinary, yet this humble experiment would reveal behavior so strange that even some of the greatest physicists struggled to fully understand its meaning. To appreciate why the results were so surprising, it helps to imagine how ordinary objects behave. Suppose someone throws small pebbles toward a wall with two gaps. Some pebbles pass through the left opening, and some through the right. On the screen behind the wall, two clusters would appear, corresponding to the positions of the two openings. This outcome matches common sense. Particles travel through one path or the other and leave traces accordingly. Now imagine replacing the pebbles with water waves. Waves spreading through both openings overlap with one another. In certain regions, the crests of the waves combine and produce stronger waves. In other regions, crests and troughs cancel each other out. The result is an interference pattern, a series of alternating bright and dark bands. Such behavior is characteristic of waves and had been observed many times with light and water. By the 19th century, experiments involving light passing through two slits clearly produced interference patterns. This strongly supported the wave theory of light. There seemed to be nothing mysterious about it. Waves interfere with waves, exactly as expected. But during the 20th century, physicists began performing similar experiments with electrons. The results were astonishing. When many electrons were fired toward the double-slit apparatus, they created the same interference pattern previously associated with waves. This suggested that electrons behaved like waves, yet each electron struck the screen at a single localized point, like a tiny particle. Over time, as more and more electrons arrived, the individual impacts gradually built up the familiar interference pattern. At first, one might imagine that electrons simply interacted with one another while traveling. To test this possibility, scientists reduced the intensity of the beam until electrons passed through the apparatus one at a time. There were never two electrons present simultaneously, and yet, even under these conditions, the interference pattern still emerged. Somehow, each electron behaved as though it interfered with itself. This result challenged the deepest assumptions of classical thinking. Through which slit did the electron travel? If it went through only one opening, no interference pattern should appear. If it somehow passed through both openings simultaneously, what exactly did that mean? Human intuition struggled to provide satisfying answers. Physicists then introduced detectors near the slits to determine which path the electrons actually took. The moment they attempted to observe the electron's route, something remarkable happened. The interference pattern disappeared. Instead of producing wave-like behavior, the electrons behaved like ordinary particles and formed two distinct clusters on the screen. Simply obtaining information about the path altered the outcome. This discovery became one of the most famous and puzzling aspects of quantum mechanics. Observation seemed to matter in a profound way. However, the word observation often creates misunderstandings. The electron does not require a conscious human being watching the experiment. A detector, another particle, or any physical interaction capable of revealing information is sufficient. Quantum systems respond not to awareness, but to interactions that extract information from them. Before measurement, the electron is described by a wave function representing multiple possible outcomes. These possibilities evolve according to precise mathematical rules. The wave spreads through both slits and generates interference. But once information about the path becomes available, the system changes. The electron no longer behaves as though both possibilities remain equally active. Exactly why this happens remains one of the deepest questions in physics. Some interpretations suggest that measurement causes a collapse of the wave function, reducing many possibilities into a single observed outcome. Other interpretations argue that all possibilities continue to exist, with reality branching into different versions. Still others propose entirely different explanations. Despite these disagreements, the mathematical predictions remain extraordinarily accurate. The mystery lies not in the calculations, but in understanding what the calculations actually mean. The double-slit experiment has been repeated with astonishing precision. Scientists have performed versions using photons, electrons, neutrons, atoms, and even relatively large molecules containing dozens of atoms. Again and again, nature delivers the same message. The microscopic world does not conform to ordinary expectations. Perhaps the most surprising aspect is that these strange effects are not rare exceptions. They are fundamental features of reality. The solid objects surrounding us, the atoms inside our bodies, and the light arriving from distant stars all obey the same quantum principles. The reason we do not notice such behavior in daily life is that large objects interact constantly with their environment, causing quantum effects to become hidden beneath layers of complexity. Richard Feynman, one of the greatest physicists of the 20th century, often remarked that the double-slit experiment contains the central mystery of quantum mechanics. In many ways, he was correct. Within this deceptively simple arrangement lies a challenge to some of humanity's oldest assumptions about reality, certainty, and the nature of existence itself. What begins as two tiny openings in a barrier ultimately leads to questions about probability, information, and the relationship between observation and the physical world. The experiment does not merely reveal unusual behavior. It invites us to reconsider what it means for something to possess a definite history, a definite path, or even a definite existence before measurement. In the quiet realm of atoms and electrons, reality seems less like a collection of fixed objects and more like a tapestry of possibilities, unfolding according to rules that are beautiful, precise, and endlessly mysterious. By the time physicists had uncovered the strange behavior revealed by the double-slit experiment, it had become increasingly clear that the microscopic world could not be described using the same ideas that worked so well for planets, baseballs, and falling rain. Classical physics was built upon certainty. If the position and speed of an object were known, its future could in principle be calculated exactly. The universe appeared to function like an enormous clock, with every movement unfolding according to precise and predictable laws. Quantum mechanics introduced a completely different perspective. Instead of certainty, it placed probability at the heart of nature. This did not mean that the theory itself was vague or imprecise. In fact, quantum mechanics is among the most accurate scientific frameworks ever created. Its equations predict experimental results with astonishing precision. The uncertainty lies not in the mathematics, but in the outcomes that nature chooses when measurements are made. To understand the shift, imagine tossing a coin. Before it lands, there are two possible outcomes, heads or tails. The probability of each is roughly equal. Once the coin lands, only one result becomes reality. In everyday life, probabilities often arise because people lack complete information. If someone knew every detail about the motion of the coin, the air around it, and the exact force applied, classical physics suggests that the outcome could, at least in principle, be predicted. Quantum probability is different. Even with complete knowledge of a quantum system, the theory does not provide absolute certainty about individual events. Instead, it predicts the likelihood of various possible outcomes. Nature itself appears to contain an element of unpredictability at its deepest level. Central to this idea is the concept of a quantum state. A quantum state contains all the information that can be known about a system. It represents the collection of possible outcomes and their associated probabilities. Unlike an ordinary object with a single definite position and velocity, a quantum system is described by a broader and more subtle mathematical structure. Consider an electron. In classical thinking, one might imagine it as a tiny ball occupying a precise location and moving along a specific path. Quantum mechanics paints a different picture. Before a measurement is made, the electron is described by a state that encompasses many possibilities. The theory does not assign a single predetermined answer. Instead, it provides a map of probabilities. This idea can feel uncomfortable because human intuition evolved in a world of large objects. People are accustomed to asking questions like, where is the object? Or what is its speed? Quantum mechanics often answers such questions in terms of possibilities rather than certainties. It is not that the theory refuses to provide information. Rather, nature itself appears to operate differently at microscopic scales. Probability enters everyday life in familiar ways. Weather forecasts estimate the chance of rain. Insurance companies calculate risks. Games of chance involve uncertain outcomes. Yet all these examples depend upon incomplete knowledge. Quantum probabilities seem more fundamental. Even with perfect preparation and perfect instruments, individual results remain unpredictable. What can be predicted with extraordinary accuracy are the statistical patterns produced by many repeated experiments. Imagine firing thousands of electrons toward a screen. Each individual impact occurs unpredictably. No equation specifies the exact point where a particular electron will arrive. Yet when enormous numbers of electrons are considered together, beautiful and highly reproducible patterns emerge. The collective behavior follows precise laws, even though individual events remain uncertain. This combination of randomness and order is one of the most remarkable features of quantum mechanics. Nature appears neither completely chaotic nor completely deterministic. Instead, it operates according to probabilities governed by mathematical rules of extraordinary elegance. Physicists eventually developed a sophisticated language for describing these states. The mathematical objects involved may seem abstract, but their predictions correspond directly to experimental reality. Every laser, transistor, and modern computer chip owes its existence to these principles. Although the equations themselves can become complex, the underlying idea remains surprisingly simple. Reality at microscopic scales is described not by certainties, but by structured possibilities. Another fascinating aspect of quantum states is that they can change. A system evolves over time according to specific equations, causing the probabilities associated with different outcomes to shift. The wave-like behavior observed in the double-slit experiment arises because these probabilities can interfere with one another. Possibilities themselves seem capable of combining and canceling, producing patterns that have no counterpart in ordinary experience. Even more strangely, two different systems can become linked in ways that cause their states to depend upon one another. Such connections lead to phenomena that puzzled even Albert Einstein and eventually became known as quantum entanglement. Long before those ideas emerged, however, physicists first had to accept that probability was not merely a practical tool, but a fundamental ingredient of the universe. This realization represented one of the greatest philosophical shifts in scientific history. For centuries, many thinkers imagined that complete knowledge would allow complete prediction. Quantum mechanics suggested otherwise. There may be limits not because humans are imperfect observers, but because nature itself is woven from possibilities. Yet, despite this uncertainty, the world remains astonishingly reliable. The sun rises, atoms remain stable, chemistry works with remarkable consistency. The probabilities involved are not signs of disorder. They are part of a deeper structure, one that gives rise to the richness and stability of the universe we inhabit. Beneath the apparent solidity of everyday life lies a realm where certainty softens into likelihood, where possibilities coexist before measurement, and where reality unfolds according to patterns that are statistical yet profoundly ordered. In this hidden landscape, probability is not a sign of ignorance. It is one of the fundamental languages through which nature expresses itself. One of the most unusual ideas introduced by quantum mechanics is the principle of superposition. To people accustomed to everyday experience, the concept can seem almost impossible to accept. In ordinary life, objects occupy definite states. A lamp is either on or off. A book rests either on the table or on the shelf. A train travels along one track and not another. Human intuition is built upon clear distinctions. Things appear to possess well-defined properties at every moment. The quantum world does not always follow these familiar rules. As physicists explored the mathematics behind atomic behavior, they discovered that quantum systems could exist in combinations of different possibilities simultaneously. Before a measurement is performed, the system does not necessarily possess a single definite state in the classical sense. Instead, it may occupy what scientists call a superposition, a blend of multiple potential outcomes described together within the wave function. To understand the idea, imagine listening to a musical chord. A chord is not a single note, but several notes sounding together. Each individual note contributes to the overall sound, and the combination creates something richer than any single tone alone. Superposition resembles this concept in a mathematical sense. Different possibilities coexist and evolve together until a measurement produces a specific result. This strange principle first emerged naturally from the equations themselves. Physicists did not invent superposition because they desired mystery. The mathematics demanded it, and experiments repeatedly confirmed its predictions. Whenever researchers ignored superposition and attempted to force classical descriptions onto microscopic systems, their calculations failed. Nature consistently behaved according to the quantum rules. Electrons provide one of the clearest examples. In an atom, an electron does not orbit the nucleus like a tiny planet circling a star. Instead, it occupies a quantum state described by a spread of probabilities. The electron behaves as though multiple possible positions contribute to its existence simultaneously. Only when an interaction or measurement occurs does one particular outcome become observed. The double-slit experiment offered another remarkable illustration. Each electron seemed to pass through both openings in a wave-like manner, producing interference patterns characteristic of superposition. Yet every individual detection appeared as a single localized event. Somehow, multiple possibilities combined before giving rise to a single observed result. As bizarre as this sounds, the principle has been demonstrated countless times. Scientists have observed superposition not only in electrons, but also in photons, atoms, and increasingly complex molecules. Experiments continue to push the boundaries, showing that quantum effects can extend to larger systems under carefully controlled conditions. One reason superposition feels so strange is that it has no obvious equivalent in everyday life. A coin spinning rapidly before it lands may appear uncertain, but classical physics assumes that its state is already determined by hidden details of its motion. Quantum superposition is different. The uncertainty is not merely a reflection of incomplete knowledge. The system itself is described by multiple possibilities at once. This idea troubled many physicists, including Albert Einstein. He believed that deeper hidden mechanisms might eventually restore a more intuitive picture of reality. Others, including Niels Bohr, argued that quantum mechanics represented a fundamentally new way of understanding nature. Their debates became some of the most famous scientific discussions of the 20th century. Perhaps the most widely known illustration of superposition emerged from a thought experiment proposed by Erwin Schrödinger. He imagined a cat sealed inside a box together with a device linked to a quantum event. According to the mathematical description, before observation, the quantum event exists in a superposition of possibilities. If one follows the equations strictly, the entire system, including the unfortunate cat, seems to become a superposition as well. Schrödinger introduced this example not because he believed cats actually occupy such bizarre states in ordinary life, but because he wished to highlight the tension between quantum mechanics and everyday experience. The thought experiment demonstrated how strange quantum principles appear when extended to larger objects. Fortunately, the world humans inhabit behaves in a far more familiar manner. Large objects constantly interact with their surroundings. Molecules collide with air particles. Light reflects from surfaces. Heat exchanges energy with the environment. These countless interactions effectively destroy delicate superpositions, causing macroscopic systems to behave according to classical expectations. This process, known as decoherence, helps explain why people do not observe cats existing in multiple conditions simultaneously. Nevertheless, superposition remains essential to understanding the microscopic world. It explains the structure of atoms, the behavior of chemical bonds, and the operation of many modern technologies. Quantum computers, one of the most exciting areas of contemporary research, rely heavily upon maintaining superpositions within carefully isolated systems. Their extraordinary computational potential arises precisely because multiple possibilities can evolve together before measurement. The principle also reveals something profound about reality itself. Nature does not seem to commit immediately to a single course of events. Instead, possibilities coexist and influence one another according to precise mathematical laws. Only when interactions occur do definite outcomes emerge. This perspective challenges the deeply rooted assumptions inherited from everyday experience. Yet it also offers a richer view of the universe. Reality, at its smallest scales, appears less like a collection of tiny solid objects following predetermined paths, and more like a delicate interplay of probabilities and possibilities. Hidden beneath the apparent certainty of the world around us lies a domain where many futures briefly coexist, where waves of possibility evolve together, and where the boundaries between what is and what might be become far more subtle than common sense would ever suggest. In that quiet and mysterious realm, superposition stands as one of the most beautiful and puzzling features of the quantum universe. As physicists gradually accepted that quantum systems could exist in superpositions of multiple possibilities, another question naturally arose. If particles are not simply tiny balls moving along precise trajectories, then what exactly are the equations of quantum mechanics describing? What is the mathematical object that contains all these probabilities and possibilities? The answer lies in one of the most important concepts in the entire theory, the wave function. At first encounter, the term wave function can sound mysterious, almost as though scientists had discovered some invisible substance filling space. In reality, the wave function is a mathematical description that contains all the information available about a quantum system. It serves as a kind of map of possibilities, encoding the probabilities of different outcomes that may occur when measurements are made. Unlike ordinary waves on water, the wave function does not represent physical ripples moving through a material medium. Ocean waves consist of water molecules rising and falling. Sound waves involve vibrating air molecules. The wave function is something more abstract. It describes the behavior of possibilities themselves. Although this idea can seem unusual, its predictions have been tested with extraordinary accuracy. Imagine standing in a dark room with a flashlight and a map. The map does not physically contain mountains, rivers, or roads. Instead, it provides information about where these things are likely to be found. In a similar sense, the wave function does not necessarily tell us exactly what reality is made of. Rather, it provides a complete description of what can be known about a quantum system and the likelihood of different observations. This interpretation became clearer through the work of the German physicist Max Born during the 1920s. Born proposed that the wave function itself should not be viewed as a material object. Instead, the square of its magnitude corresponds to probability. In other words, the wave function tells us how likely it is to find a particle in various locations or states when a measurement occurs. This insight transformed quantum mechanics. Before Born's interpretation, many scientists struggled to understand what the strange waves represented. Were electrons literally spread throughout space like clouds? Were they hidden particles accompanied by invisible vibrations? Born's proposal shifted the focus away from physical pictures and toward measurable probabilities. The wave function became a tool for predicting outcomes, rather than a direct image of reality. Consider an electron inside an atom. Classical intuition suggests that the electron should orbit the nucleus like a miniature planet circling a star. Yet experiments reveal a very different picture. The wave function predicts regions where the electron is more likely to be found, and regions where it is less likely. These regions are called orbitals, although they differ greatly from planetary orbits. Instead of tracing a narrow path, the electron exists within a distribution of possibilities. This probabilistic picture explains many properties of matter. The arrangement of electrons determines the structure of atoms, the formation of chemical bonds, and the behavior of molecules. Every object visible around us owes its stability to these wave functions. The wood of a table, the oxygen in the air, and the calcium in human bones all derive their properties from quantum states described in this way. One of the most remarkable features of the wave function is that it evolves smoothly over time. This evolution is governed by the Schrödinger equation, one of the central equations of quantum mechanics. The equation predicts how probabilities change and how superpositions develop. Like a conductor guiding an orchestra, the Schrödinger equation determines how the many possibilities represented by the wave function unfold. Despite the extraordinary success of the mathematics, the deeper meaning of the wave function remains a subject of debate. Some physicists regard it as merely a tool for organizing information about observations. In this view, the wave function represents knowledge rather than physical reality itself. Others believe that the wave function corresponds to something genuinely real, though perhaps unlike anything encountered in ordinary experience. These different perspectives lead to various interpretations of quantum mechanics. Some suggest that the wave function collapses during measurement. Others propose that every possibility described by the wave function continues to exist in branching realities. Still others argue that hidden mechanisms may lie beneath the mathematics. Remarkably, despite their philosophical differences, these interpretations often produce identical experimental predictions. The mystery surrounding the wave function has fascinated generations of scientists. Albert Einstein, although instrumental in the development of quantum theory, remained uncomfortable with its probabilistic implications. He hoped that a deeper explanation would someday emerge. Niels Bohr, by contrast, believed that the wave function and its probabilities represented the limits of what nature allows us to know. Their discussions became legendary, reflecting not merely technical disagreements, but different visions of reality itself. Modern experiments continue to confirm the astonishing accuracy of wave functions. Lasers, semiconductors, magnetic resonance imaging, and countless other technologies rely upon calculations based on these mathematical objects. Quantum chemistry, which explains the behavior of molecules and materials, depends entirely upon solving wave functions for systems containing many particles. Yet for all their practical success, wave functions retain an air of mystery. They are neither tangible objects nor simple waves in the ordinary sense. They exist within a mathematical framework that captures possibilities with extraordinary precision, while leaving open profound questions about the nature of reality itself. Perhaps this mystery is part of what makes quantum mechanics so captivating. The theory does not merely provide answers. It invites us to reconsider the relationship between mathematics and the physical world. It suggests that beneath the familiar certainty of everyday life lies a deeper layer where probabilities replace rigid paths, where possibilities evolve according to elegant equations, and where reality may be far richer and more subtle than human intuition was ever designed to imagine. By the middle of the 20th century, physicists had become increasingly comfortable using the equations of quantum mechanics. The mathematics worked beautifully. Experiments agreed with predictions to an extraordinary degree. Yet beneath this remarkable success, a deeper question remained unresolved. What actually happens when a measurement is made? At first glance, the question seems straightforward. In everyday life, measuring something appears simple and harmless. A thermometer reveals temperature. A ruler provides length. Clock displays time. These instruments seem to uncover properties that already exist. Classical physics assumes that objects possess definite characteristics whether or not anyone chooses to observe them. Quantum mechanics introduces a much stranger picture. Before measurement, a quantum system is described by a wave function containing multiple possible outcomes. The wave function evolves smoothly and predictably according to the Schrödinger equation. Everything proceeds continuously, almost like the spreading ripples on the surface of a pond. Yet when a measurement occurs, only one specific result is observed. The many possibilities represented by the wave function somehow give way to a single outcome. This transition became known as wave function collapse. Imagine rolling a perfectly balanced die hidden beneath a cup. Classical thinking assumes that the die has already landed on a particular number, even before the cup is lifted. Looking merely reveals the answer. Quantum mechanics paints a more subtle picture. Prior to measurement, the system is not necessarily described by one hidden result waiting to be discovered. Instead, it exists in a state involving multiple possibilities. Measurement appears to transform those possibilities into one definite reality. Exactly how this transformation occurs remains one of the deepest mysteries in modern science. One of the pioneers of quantum theory, Niels Bohr, argued that the question itself might be misguided. According to his view, physics should concern itself with observable results, rather than attempts to describe some hidden reality beneath them. The wave function, in this interpretation, provides probabilities for possible measurements. Asking what happens between measurements may simply go beyond the limits of meaningful scientific language. Albert Einstein found this answer deeply unsatisfying. He believed that physical reality should exist independently of observation. To Einstein, the moon did not vanish when nobody looked at it. He suspected that quantum mechanics might be incomplete and that some deeper level of description remained undiscovered. Their disagreement became one of the most famous debates in scientific history. Adding to the mystery was the fact that the word observation itself often created misunderstandings. Popular culture sometimes suggested that consciousness, or human awareness, somehow caused collapse. This interpretation captured imaginations but lacked strong support from experiments. In modern physics, measurement does not require a person watching an apparatus. Any interaction capable of transferring information can serve the same purpose. For example, if an electron interacts with a detector, another particle, or even surrounding molecules, information about its state becomes encoded in the environment. Human beings need not be involved at all. Nature itself constantly performs countless interactions. Measurement is not necessarily an act of conscious awareness, but a physical process involving information exchange. Still, this explanation raises further questions. Why should interactions lead to definite outcomes? What distinguishes a measurement from ordinary evolution, described by the Schrödinger equation? Why does the smooth wave function appear to give rise to a single observed result? Different interpretations attempt to answer these questions in different ways. The Copenhagen interpretation, associated largely with Bohr and Werner Heisenberg, accepts collapse as a fundamental feature of nature. The wave function evolves continuously until measurement occurs, at which point probabilities become actual observations. This interpretation became enormously influential because it provided a practical framework for calculations, even if it left philosophical questions unresolved. Another approach, proposed by Hugh Everett in the 1950s, rejects collapse altogether. According to the many worlds interpretation, every possible outcome described by the wave function continues to exist. Rather than one reality being selected, the universe itself branches into multiple versions corresponding to different outcomes. Each branch contains observers experiencing one particular result. From within any single branch, reality appears definite, even though all possibilities persist. Still, other interpretations introduce hidden variables, spontaneous collapses, or entirely new mechanisms. Despite their differences, they all reproduce the same experimental predictions. This remarkable situation means that physics currently possesses extraordinary mathematical precision while lacking universal agreement regarding what the equations truly mean. Modern experiments have added further layers to the mystery. Researchers have demonstrated phenomena involving delayed choices and quantum erasers, experiments that seem to blur distinctions between past and future descriptions. These results do not violate causality or allow information to travel backward in time, but they reveal how subtle and counterintuitive the process of measurement can be. Fortunately, the strange behavior of quantum systems becomes largely invisible in everyday life. Large objects constantly interact with their environments. Air molecules, thermal radiation, and countless microscopic disturbances rapidly spread information throughout the surroundings. This process, called decoherence, suppresses observable quantum effects and gives rise to the familiar classical world people experience each day. Yet the fundamental question remains: does the wave function truly collapse? Is collapse merely an apparent phenomenon arising from larger processes? Do all possibilities continue to exist simultaneously? Or does some deeper theory await discovery? More than a century after the birth of quantum mechanics, scientists still do not possess a universally accepted answer. The equations themselves are among the most successful ever devised, but their meaning continues to inspire debate, curiosity, and wonder. Perhaps that uncertainty is part of the beauty of science. Sometimes understanding advances not by eliminating mysteries, but by learning how to ask better questions. In the quiet realm of atoms and probabilities, measurement stands as a doorway between possibility and experience, between mathematical descriptions and the realities that eventually emerge from them. It is here, in this delicate transition, that quantum mechanics reveals some of its deepest and most fascinating secrets. For much of human history, the universe was imagined as a perfectly predictable machine. If someone possessed enough information about the position and motion of every object, then in principle the future could be calculated with complete certainty. This idea reached its highest expression during the age of classical physics. The motions of planets, the paths of falling objects, and even the behavior of mechanical clocks appeared to follow precise and deterministic laws. Uncertainty, according to this view, arose only because human knowledge was incomplete. Quantum mechanics challenged that assumption in a profound and unexpected way. During the 1920s, the German physicist Werner Heisenberg discovered that there are fundamental limits to how precisely certain properties can be known at the same time. This principle became known as the uncertainty principle, and it remains one of the most famous and misunderstood ideas in all of science. In popular discussions, uncertainty is sometimes described as a consequence of measurement disturbing the system. For example, one might imagine trying to locate an electron by shining light upon it. The light itself would interact with the electron and alter its motion. While this explanation contains an element of truth, it does not capture the deeper meaning of Heisenberg's discovery. The uncertainty principle is not merely a technological limitation. It is woven into the structure of reality itself. At its heart lies a relationship between pairs of physical quantities. The most famous pair consists of position and momentum. Position describes where something is located, while momentum relates to its motion. Heisenberg showed that the more precisely one of these quantities is defined, the less precisely the other can be known. This relationship is not due to imperfect instruments or careless experiments. Even with ideal equipment and perfect conditions, the limitation remains. This simple expression captures one of the deepest truths discovered by modern physics. It tells us that nature itself imposes limits upon simultaneous precision. The universe does not always provide exact answers to every question we might wish to ask. To appreciate how strange this idea is, consider everyday objects. A moving car has both a location and a speed. In principle, these values can be measured with enormous accuracy. Any uncertainty arises because of practical limitations. But at the quantum level, particles do not possess perfectly defined values for both quantities simultaneously. Instead, their properties are distributed according to probabilities encoded within the wave function. Imagine trying to confine an electron to an extremely small region of space. As the position becomes more narrowly defined, the uncertainty in momentum grows larger. The electron's motion becomes increasingly unpredictable. Conversely, if its momentum is specified very precisely, the electron becomes spread out over a larger region. Nature seems to insist upon this balance. This principle has enormous consequences. Without it, atoms themselves would not be stable. Classical physics predicted that electrons orbiting a nucleus should gradually lose energy and collapse inward. Yet because of the uncertainty principle, electrons cannot simply fall into the nucleus and remain perfectly still. Confining them to such a tiny region would produce enormous uncertainties in momentum and energy. The resulting quantum behavior allows atoms to maintain stable structures. Everything around us depends upon this balance. The solidity of matter, the existence of chemistry, and the formation of molecules all rely upon the uncertainty principle. In a very real sense, the world humans inhabit exists because nature refuses to permit perfect precision. Uncertainty extends beyond position and momentum. Similar relationships exist for other quantities. Energy and time form another important pair. Angular momentum and orientation exhibit comparable constraints. Throughout quantum mechanics, certain properties are linked by these fundamental limitations. One remarkable consequence is the existence of quantum fluctuations. Even empty space cannot remain completely calm. Tiny variations in energy continuously arise and disappear due to the uncertainty principle. The vacuum itself is not truly empty, but contains restless activity occurring on unimaginably small scales. These fluctuations play important roles in particle physics and may even influence some aspects of cosmology. Werner Heisenberg himself recognized the philosophical significance of his discovery. For centuries, scientists had sought absolute certainty. Quantum mechanics suggested that uncertainty is not a sign of ignorance, but an intrinsic feature of the universe. Reality at microscopic scales possesses a subtle flexibility that resists complete specification. Albert Einstein found this difficult to accept. He famously remarked that God does not play dice with the universe. He hoped that deeper hidden mechanisms might someday restore determinism. Yet decades of increasingly sophisticated experiments have repeatedly confirmed the predictions of quantum mechanics. The uncertainty principle has survived every challenge. Importantly, uncertainty does not imply chaos or disorder. The laws governing quantum systems remain highly structured and mathematically precise. Although individual outcomes may be unpredictable, statistical patterns emerge with extraordinary reliability. Randomness and order coexist in a delicate balance, giving rise to the stable and predictable world people experience on larger scales. In everyday life, the effects of the uncertainty principle are hidden because the masses and dimensions involved are so large. The uncertainties associated with cars, mountains, and planets are unimaginably tiny compared to their overall properties. As a result, classical physics provides an excellent approximation. Only when scientists probe the microscopic realm do the deeper quantum rules reveal themselves. Perhaps the uncertainty principle teaches something broader about the nature of knowledge itself. Human intuition often seeks complete answers and perfect descriptions. Yet the universe appears to possess an irreducible subtlety. Certain questions cannot be answered with unlimited precision, not because people are incapable, but because reality itself is more nuanced than classical ideas once suggested. Far from representing a flaw in nature, this uncertainty gives rise to richness, stability, and possibility. It allows atoms to exist, chemistry to flourish, and stars to shine. Beneath the apparent certainty of everyday life lies a world where precision has limits, where probabilities replace absolutes, and where the quiet mystery of uncertainty helps shape the very fabric of existence. Once the uncertainty principle revealed that nature imposes fundamental limits on precision, physicists began to understand why atoms do not behave like miniature solar systems. Classical physics had imagined electrons orbiting a nucleus in smooth, continuous paths, much like planets circling a star. But this picture could not survive in the quantum world. Instead, atoms revealed a deeply structured internal organization governed by discrete patterns described through what are known as quantum numbers. The story of atomic structure begins with a simple observation. When elements are heated or energized, they emit light at very specific wavelengths. Hydrogen, for example, produces a characteristic set of spectral lines rather than a continuous glow. Each element behaves like a fingerprint of light with its own unique pattern. These patterns suggested that electrons inside atoms were not free to take any arbitrary energy value. Instead, they were restricted to specific allowed states. Quantum mechanics explained this restriction through the concept of quantization. Rather than existing in a continuous range of energies, electrons occupy discrete levels. These levels are not random. They arise naturally from the wave-like nature of electrons and the constraints imposed by their interaction with the atomic nucleus. Inside an atom, an electron is described by a wave function that must satisfy strict mathematical conditions, like a vibrating string that can only produce certain harmonics. An electron bound to a nucleus can only form specific standing wave patterns. Each allowed pattern corresponds to a distinct energy state. These states are labeled using quantum numbers, which serve as a kind of address system for electrons inside atoms. The first and most important of these is the principal quantum number. It determines the overall energy level and size of the electron's distribution around the nucleus. Higher values correspond to states where the electron is, on average, farther from the nucleus and has greater energy. These energy levels are arranged in a structured hierarchy, somewhat like floors in a building, though the quantum reality is far more abstract. Within each principal level, additional structure appears. The angular momentum quantum number describes the shape of the electron's probability distribution instead of simple circular orbits. Electrons occupy regions in space that can resemble spheres, dumbbells, and more complex forms. These shapes arise naturally from the wave nature of electrons and the requirement that their wave functions remain stable and consistent around the nucleus. A third quantum number, the magnetic quantum number, describes how these shapes are oriented in space, even though the atom itself may be isolated. External influences such as magnetic fields can distinguish between different orientations. This adds another layer of structure to the atomic architecture. Finally, there is the spin quantum number, a deeply quantum property with no true classical analog. Spin does not refer to physical rotation in the ordinary sense. Instead, it represents an intrinsic form of angular momentum carried by particles. Electrons behave as if they possess a built-in rotational characteristic that can take only specific values. This property plays a crucial role in determining how electrons arrange themselves inside atoms. Together, these quantum numbers form a complete description of the allowed states of electrons in atoms. They are not arbitrary labels. They arise directly from the mathematical structure of quantum mechanics and the wave-like behavior of matter. One of the most important consequences of this structure is the organization of the periodic table. Each chemical element corresponds to a different arrangement of electrons among the available quantum states. As electrons fill lower energy levels, they begin to occupy higher ones, creating the repeating patterns of chemical behavior observed across elements. The familiar periodic trends in reactivity, bonding, and stability all emerge from this underlying quantum architecture. Without quantum mechanics, the periodic table would appear mysterious and disconnected. With it, the table becomes a natural consequence of wave functions confined within atomic boundaries. The richness of chemistry, from the formation of water molecules to the complexity of organic compounds, is ultimately rooted in these quantum rules. Another important implication is atomic stability. Electrons cannot simply spiral into the nucleus because they are restricted to allowed quantum states. The lowest possible state, known as the ground state, still involves motion and uncertainty. Even at absolute zero temperature, electrons retain a minimum amount of energy, a direct consequence of the uncertainty principle and the structure of wave functions. This prevents matter from collapsing and ensures the stability of atoms. As atoms combine to form molecules, quantum numbers continue to guide their behavior. Chemical bonds form when electron wave functions overlap and reorganize into new stable configurations. These interactions determine the shapes of molecules, the properties of materials, and the mechanisms of chemical reactions. Everything from the hardness of diamond to the flexibility of biological molecules emerges from these quantum rules. It is remarkable that such a vast range of physical and chemical phenomena can be traced back to a relatively small set of mathematical principles. Quantum numbers, born from wave functions and constrained by uncertainty, provide the structural blueprint of matter itself. In this sense, atoms are not simple collections of particles, but highly organized systems of quantum states. Their architecture is not built from solid parts, but from patterns of probability that remain stable over time. What appears as solid matter in everyday life is, at its deepest level, a carefully balanced arrangement of wave functions governed by elegant mathematical rules. As the study of quantum mechanics continues, this hidden architecture reveals ever more layers of complexity and beauty. Beneath the surface of the visible world lies a structured quantum order, quietly shaping everything that exists. Once quantum numbers revealed the hidden structure inside atoms, physicists began to see that electrons do not move through space in the way classical intuition suggests. Instead of following neat circular paths around a nucleus, electrons exist in extended probability patterns that define where they are likely to be found. These patterns are called orbitals, and they form the true architectural framework of matter. In classical physics, an orbit was simple. A planet circles a star along a predictable trajectory, and at any given moment its position and velocity are well defined. Early models of the atom borrowed this image, imagining electrons as tiny charged objects orbiting a dense nucleus. But this picture quickly failed. According to classical electromagnetism, an accelerating charged particle should continuously emit radiation and lose energy. Electrons should spiral inward and collapse into the nucleus almost instantly. Yet atoms are stable, and matter persists. Quantum mechanics resolved this contradiction in a radically different way. Electrons are not localized particles moving along fixed paths. They are described by wave functions that occupy regions of space, forming standing wave structures around the nucleus. These structures are the orbitals, and each one corresponds to a specific energy level defined by quantum numbers. An orbital is not a physical shell or a cloud of particles. It is a mathematical description of probability. It tells us where an electron is likely to be found if a measurement is made. Some regions have high probability, others have low probability, and some are essentially forbidden. Over time, the wave function remains stable, creating patterns that persist as long as the system is not disturbed. The simplest orbital is the spherical s orbital. It surrounds the nucleus evenly in all directions, forming a symmetrical probability distribution. As energy increases, more complex shapes appear. P orbitals take on a dumbbell shape, with two regions of high probability separated by a nodal plane where the probability drops to 0. Even more complex orbitals, labeled D and F, display intricate structures with multiple lobes and nodes. These shapes arise naturally from the mathematical solutions to the Schrödinger equation in three-dimensional space. Each orbital represents a stable configuration of the electron's wave function. Stability arises because only certain wave patterns are allowed. Much like a guitar string can only vibrate at specific frequencies, electrons in an atom can only occupy certain standing waveforms. Any attempt to force an electron into a forbidden configuration would violate the conditions required for a stable wave solution. This wave nature of electrons explains why matter has structure, instead of collapsing into a featureless lump. Atoms maintain distinct sizes and shapes because electrons occupy orbitals that resist compression. The uncertainty principle plays a crucial role here. Confining an electron too tightly would increase its momentum uncertainty, creating energetic resistance that prevents collapse. As a result, atoms maintain a balance between localization and motion. When atoms interact, their orbitals overlap and combine. This process leads to the formation of chemical bonds. In a hydrogen molecule, for example, two hydrogen atoms share electrons in a combined orbital structure that lowers the overall energy of the system. This sharing is not like two tiny objects exchanging positions. Instead, it is a merging of wave functions into a new stable pattern that extends across both nuclei. More complex molecules arise from similar principles. Carbon, with its ability to form 4 bonds, becomes the foundation of organic chemistry because of the way its orbitals can hybridize into different configurations. These quantum interactions determine the shapes of proteins, the structure of DNA, and the behavior of all known biological systems. Life itself is deeply rooted in the geometry of electron orbitals. Another important consequence of orbital structure is the exclusion principle, introduced by Wolfgang Pauli. It states that no two electrons in the same atom can occupy the same quantum state simultaneously. This principle explains why electrons fill orbitals in a specific order and why matter does not collapse into identical configurations. Without it, atoms would behave very differently, and the diversity of chemical elements would not exist. As electrons fill orbitals from lower to higher energy levels, they create the repeating patterns observed in the periodic table. Elements in the same column share similar outer electron configurations, which leads to similar chemical behavior. This periodic structure is not arbitrary. It is a direct consequence of how orbitals are arranged within atoms. On a deeper level, orbitals show that matter is not built from hard particles, but from stable patterns of probability. What we perceive as solid objects are actually the result of countless overlapping wave functions, forming persistent structures. The sensation of solidity emerges from electromagnetic interactions between these quantum states, not from rigid physical boundaries. Even the surfaces of objects are not truly solid in the classical sense. They are regions where electron orbitals repel each other, preventing atoms from passing through one another. The feeling of touching a table is the result of quantum mechanical repulsion between orbitals in your hand and those in the object. At the deepest level, contact is not a collision of hard particles, but an interaction between probability structures. Orbitals also explain why matter has volume, why materials have different strengths and flexibilities, and why chemistry produces such an enormous variety of substances. Everything from metals to gases to living tissue arises from the same underlying quantum rules applied to different orbital configurations. In this way, electrons and orbitals form the hidden framework of the physical world. They are not visible to the eye, yet they determine the shape, stability, and behavior of everything we see. Beneath the apparent solidity of reality lies a delicate pattern of wave functions, quietly maintaining the structure of the universe. As the structure of atoms became clearer through orbitals and quantum numbers, physicists encountered another property of electrons that refused to fit into any classical picture. This property was called spin, and although the name suggests something like rotation, it is not rotation in any ordinary sense. Spin is one of the most fundamental features of quantum particles, yet it has no direct counterpart in everyday experience. At first, scientists tried to interpret spin as if electrons were tiny spheres physically spinning around their own axis. This idea was tempting because it provided a familiar mental image. However, it quickly ran into problems. If electrons were literal spinning objects, the surface would need to move faster than the speed of light to produce the observed magnetic effects. This contradiction showed that the simple picture could not be correct. Instead, spin must be understood as an intrinsic form of angular momentum, built into the identity of the particle itself. It is not caused by motion through space. It is not the result of parts rotating. It is a fundamental quantum property, as basic as charge or mass. One of the most important discoveries about spin is that it is quantized. Electrons do not have arbitrary spin values. Instead, they can only take specific, discrete orientations when measured along a chosen axis. In the simplest case, an electron has two possible spin states, often described as up or down. These are not directions in space in the classical sense, but outcomes of measurement. This discreteness connects spin directly to the quantum structure of matter. When electrons occupy orbitals, their spin plays a crucial role in determining how they can arrange themselves. Because of the Pauli exclusion principle, two electrons in the same orbital must have opposite spins. This restriction helps shape the entire structure of the periodic table and ensures the stability of complex atomic systems. Spin also gives electrons a magnetic moment. Even though electrons are not literally spinning spheres, they behave as if they are tiny magnets. When placed in a magnetic field, their spin states interact with the field and produce measurable effects. This behavior allows scientists to detect and manipulate spin experimentally, confirming its reality as a physical property rather than a mathematical abstraction. One of the most famous experiments demonstrating spin is the Stern-Gerlach experiment. In this setup, a beam of atoms is passed through a non-uniform magnetic field. Classical physics would predict a continuous spread of deflections depending on random orientations of atomic magnets. Instead, the beam splits into discrete paths. This result shows that angular momentum at the quantum level is quantized, and that spin can only take specific values. The implications of spin extend far beyond atomic physics. In chemistry, spin determines how electrons pair up in orbitals and influences the magnetic properties of materials. Some substances become strongly magnetic because many electron spins align in the same direction, while others remain non-magnetic due to cancellation of spin orientations. In more advanced physics, spin becomes even more fundamental. Different types of particles are classified according to their spin values. Electrons, protons, and neutrons have half-integer spin, while photons have integer spin. This distinction leads to a deep division in the quantum world between fermions and bosons. Fermions obey the exclusion principle and form matter, while bosons can occupy identical states and often act as force carriers. This classification shapes the entire structure of reality. Matter exists in stable forms because fermions cannot collapse into the same quantum state. Forces such as light and electromagnetism arise from bosons, which can act collectively in coherent states like lasers. Spin, therefore, plays a central role in determining both the structure of matter and the behavior of interactions. Despite its importance, spin remains one of the most non-intuitive aspects of quantum mechanics. It does not correspond to anything visible in the macroscopic world. It is not motion, not orientation in space, and not a hidden classical rotation. It is something deeper, a purely quantum property that only reveals itself through measurement outcomes and mathematical structure. In modern physics, spin is described using sophisticated mathematical frameworks that extend beyond simple three-dimensional intuition. These descriptions predict experimental results with extraordinary accuracy, even though the underlying reality resists visualization. Spin behaves consistently and predictably in experiments, yet its true nature remains abstract. This tension between mathematical precision and intuitive mystery is a recurring theme in quantum mechanics. Spin exemplifies it perfectly. It is a property that can be measured, manipulated, and used in technology, yet it defies simple explanation in terms of everyday experience. From quantum computing to magnetic resonance imaging, spin has become a practical tool in modern science. It allows information to be stored, detected, and controlled at the quantum level. In this way, something so strange and abstract becomes a foundation for real-world applications. Spin reminds us that the quantum world is not merely a smaller version of classical physics. It is a different framework altogether, where properties can exist without classical analogs, and where reality follows rules that often challenge intuition. Beneath the familiar world of shapes and motions lies a deeper structure, where even the idea of rotation must be reimagined in entirely new terms. As quantum mechanics continued to unfold, physicists discovered another behavior that seemed impossible from the perspective of classical physics. It involved particles crossing barriers that, according to everyday logic, they should never be able to pass. This phenomenon is known as quantum tunneling, and it reveals just how different the quantum world is from the macroscopic world of intuition and experience. In classical physics, motion is governed by energy constraints. If a ball rolls toward a hill and does not have enough energy to reach the top, it will inevitably roll back down. The barrier is absolute. Without sufficient energy, passage is impossible. This idea is deeply rooted in everyday experience. Walls block movement. Hills restrict motion. Energy determines what is possible and what is not. Quantum mechanics introduces a more subtle picture. Particles such as electrons are not described as single points moving along precise paths. Instead, they are represented by wave functions that extend through space. When a particle encounters an Inouye barrier, its wave function does not simply stop at the edge. Instead, it begins to decay inside the barrier. In some cases, a small portion of the wave function can extend through to the other side. This means there's a non-zero probability that the particle can appear beyond the barrier, even if it does not have enough classical energy to overcome it. This effect is not a violation of energy conservation. Instead, it arises from the probabilistic nature of quantum states and the uncertainty principle. The particle does not borrow energy in a classical sense. Rather, its existence is described by a distribution of possibilities, and those possibilities include outcomes that would be forbidden in classical reasoning. To understand this more intuitively, imagine a wave approaching a thick wall. In classical wave physics, such as sound or water waves, some energy can sometimes pass through a barrier depending on its properties. Quantum waves behave similarly, but with a crucial difference. The wave function represents probabilities rather than physical displacement. Where the wave function exists beyond the barrier, there is a chance of detecting the particle there. If a measurement is performed on the far side of the barrier and the particle is found, it appears as though it has passed through a solid obstacle without going over it. This is tunneling. The probability of tunneling depends strongly on the width and height of the barrier and the mass of the particle. Very light particles like electrons can tunnel relatively easily under the right conditions. Heavier objects, such as baseballs or even molecules at macroscopic scales, have effectively zero probability of tunneling through ordinary barriers. This is why tunneling is not noticeable in everyday life, even though it is constantly happening at microscopic scales. One of the most important real-world consequences of quantum tunneling is nuclear fusion in stars. Inside the cores of stars, positively charged nuclei repel each other due to electromagnetic forces. According to classical physics, the temperatures required to overcome this repulsion would need to be much higher than what stars actually possess. Yet fusion occurs anyway. Quantum tunneling allows particles to pass through the energy barrier created by electrostatic repulsion, enabling nuclear reactions that power the sun and other stars. Without tunneling, stars as we know them could not exist. Another important application is in modern electronics. Devices such as tunnel diodes and scanning tunneling microscopes rely directly on this effect. In a scanning tunneling microscope, a sharp probe is brought extremely close to a surface without touching it. Electrons tunnel between the probe and the surface, creating a measurable current. By analyzing this current, scientists can reconstruct images of individual atoms on a surface with remarkable precision. Tunneling also plays a role in nuclear decay processes, such as alpha decay, where particles escape from atomic nuclei by tunneling through potential barriers. This process determines the stability and lifetime of certain radioactive elements. Despite its practical importance, tunneling remains deeply counterintuitive. It suggests that barriers in quantum mechanics are not absolute in the way they are in classical physics. Instead, they are regions where the probability of existence decreases, but never becomes strictly zero. Given enough time or enough particles, even extremely unlikely events can occur. This does not mean that particles randomly ignore physical laws. Rather, it reflects the underlying probabilistic structure of quantum mechanics. The wave function evolves in a way that allows for small but real possibilities of barrier penetration. These possibilities are not classical trajectories, but mathematical features of the quantum description. Quantum tunneling, therefore, represents another example of how quantum mechanics reshapes fundamental ideas about motion and possibility. In a quantum world, objects do not simply move over or around obstacles. They exist as distributions of probability that can extend into forbidden regions and, under the right conditions, emerge on the other side. What appears impossible in the macroscopic world becomes not only possible but essential in the microscopic one. Tunneling shows that reality at small scales is governed not by rigid boundaries, but by flexible probabilities that allow the universe to behave in ways that classical intuition could never predict. As quantum mechanics matured, it began revealing effects that challenged even the idea that objects in space are truly independent from one another. Among the most striking of these effects is quantum entanglement, a phenomenon where two or more particles become linked in such a way that their properties remain connected, no matter how far apart they are later separated. In classical thinking, objects influence each other only through direct interaction or through signals that travel across space. If two coins are placed in separate rooms, flipping one coin cannot instantly affect the outcome of the other. Physical influence requires time, distance, and a connecting mechanism. This assumption feels natural because it matches everyday experience. Quantum mechanics introduces a different structure. When particles interact under certain conditions, their quantum states can become entangled. This means that the combined system must be described as a single unified wave function, even if the particles later move far apart. Their properties are no longer independent. Instead, the system contains correlations that persist regardless of distance. Imagine two electrons created in a shared process. Before they separate, their combined state is defined as a single quantum object. After they move apart, perhaps across opposite sides of a laboratory or even across galaxies, the system remains described by one entangled wave function. Measuring one particle immediately determines the outcome of measurements on the other. According to the structure of the shared state, this does not mean that information travels faster than light. No usable signal can be sent through entanglement alone. The outcomes of individual measurements remain fundamentally random. However, the correlations between the outcomes are stronger than anything allowed by classical physics. This feature puzzled many physicists, including Albert Einstein, who famously referred to it as spooky action at a distance. He found it difficult to accept that the properties of one particle could appear to depend on measurements performed on another distant particle without any physical interaction traveling between them. Einstein believed that some hidden explanation must exist beneath the surface of quantum mechanics. To explore this issue more deeply, physicists developed mathematical inequalities that could distinguish between classical and quantum predictions. These are known as Bell inequalities, named after physicist John Bell. Experiments conducted over the past several decades have consistently shown that quantum mechanics violates these classical constraints. The correlations predicted by entanglement are real and have been repeatedly confirmed in laboratory settings. One of the most important aspects of entanglement is that it is not limited to small systems or special conditions. Photons, electrons, atoms, and increasingly complex systems can become entangled under the right circumstances. Scientists have even created entangled states involving large numbers of particles in carefully controlled experiments. However, maintaining entanglement becomes more difficult as systems interact with their environment, a process related to decoherence. Entanglement has profound implications for how reality is understood. It suggests that the universe cannot always be described as a collection of independent objects with their own separate properties. Instead, the fundamental description may involve relationships and correlations that extend across space. In an entangled system, it is not meaningful to assign complete properties to each particle individually before measurement. The properties exist only as part of the whole system. Only when measurements are made do specific outcomes appear, and these outcomes are correlated in precise and predictable ways. This idea challenges classical intuition, where objects are assumed to have definite properties regardless of observation. In the quantum picture, the relationships between objects can be more fundamental than the objects themselves. Entanglement also plays an important role in modern physics and technology. It forms the foundation of quantum information science, including quantum computing, quantum cryptography, and quantum teleportation protocols. These technologies do not rely on transmitting matter itself across space instantaneously, but on manipulating shared quantum states to perform tasks that are impossible in classical systems. Quantum cryptography, for example, uses entangled particles to create communication systems that are theoretically secure against eavesdropping. Any attempt to observe the system disturbs the entanglement and reveals the presence of an intruder. In this way, the strange features of quantum mechanics become useful tools for information security. At a deeper level, entanglement suggests that space itself may not be the most fundamental aspect of reality. Instead, relationships between quantum states might form the underlying structure from which spatial separation emerges. Some modern theories in physics explore the idea that space is built from patterns of entanglement rather than existing as a fixed backdrop. Although these ideas remain under active investigation, entanglement already stands as one of the most experimentally verified and conceptually challenging aspects of quantum mechanics. It reveals a world where separation does not necessarily imply independence, and where distant objects can remain linked through shared quantum structure. In this quiet and interconnected framework, the universe behaves less like a collection of isolated pieces and more like a single, deeply connected system, where relationships persist even across vast stretches of space. As quantum mechanics developed into a complete mathematical theory, it did not immediately settle the question of what reality actually is. Instead, it opened one of the most famous intellectual disagreements in the history of science. At the center of this debate stood two towering figures, Albert Einstein and Niels Bohr, each representing a different vision of the physical world. Einstein approached physics with a deep commitment to realism and determinism. He believed that the universe should exist in a well-defined state at all times, independent of observation. In his view, physical properties such as position, momentum, and energy should have definite values whether or not anyone measures them. The role of physics, according to Einstein, was to uncover this underlying reality. Quantum mechanics, however, seemed to challenge this viewpoint. The theory described systems in terms of probabilities and wave functions, with outcomes that only become definite during measurement. To Einstein, this suggested that quantum mechanics might be incomplete. He suspected that hidden variables, not yet discovered, could restore a more classical picture of certainty beneath the probabilistic surface. Niels Bohr held a very different perspective. He argued that quantum mechanics was not incomplete, but instead fundamentally correct in its present form. According to Bohr, physics does not describe an objective reality independent of observation in the classical sense. Instead, it provides a framework for predicting experimental outcomes. The wave function, in this view, is not a picture of what exists in space, but a tool for calculating probabilities of what can be observed. This difference in interpretation led to deep and often philosophical discussions between the two scientists. They debated not only technical aspects of physics, but also the meaning of reality itself. Their conversations became legendary, often taking place during scientific conferences where other physicists listened carefully as the foundations of modern physics were questioned. One of Einstein's most famous objections to quantum mechanics involved entanglement and the idea of instantaneous correlations across distance. He argued that if quantum theory were complete, it would imply effects that seemed to conflict with locality, the principle that objects should only be influenced by their immediate surroundings. Bohr responded by emphasizing that quantum correlations do not transmit usable information faster than light, and that the theory remains consistent within its own framework. To challenge quantum mechanics further, Einstein, along with collaborators Boris Podolsky and Nathan Rosen, proposed a thought experiment known as the EPR paradox guide. This argument was designed to show that quantum mechanics either violates locality or fails to provide a complete description of reality. The EPR paper concluded that some deeper theory must exist that restores classical notions of physical reality. For many years, the debate remained largely philosophical. Quantum mechanics worked perfectly in experiments, yet its interpretation remained unsettled. It was not until decades later that experimental physics began to address these questions directly. The introduction of Bell's theorem provided a way to test whether hidden variable theories consistent with classical ideas could reproduce the predictions of quantum mechanics. Experiments based on these ideas consistently supported quantum theory and ruled out large classes of classical alternatives. The results showed that nature does not obey all the assumptions underlying Einstein's intuition about locality and realism. at least not in the classical sense. Despite these experimental outcomes, the debate did not disappear. Instead, it evolved into a richer set of interpretations. Some physicists adopted the Copenhagen interpretation associated with Bohr, accepting probability and measurement as fundamental elements of nature. Others explored many worlds interpretations, hidden variable theories, or objective collapse models, each attempting to explain quantum behavior in different ways. What makes this situation unique in physics is that all major interpretations agree on the mathematical structure and experimental predictions of quantum mechanics. They differ not in what the theory calculates, but in what it means. In most areas of science, disagreement is resolved by new data. In quantum foundations, the data is already extremely precise, yet multiple philosophical frameworks remain viable. This creates a rare situation where physics and philosophy overlap deeply. The equations of quantum mechanics are among the most successful ever created, yet their interpretation touches questions about reality, observation, and existence itself. The debate between Einstein and Bohr represents not only a scientific disagreement, but a reflection of two different ways of understanding the universe. Einstein's vision emphasized an objective reality that exists independently of observation, governed by underlying deterministic laws. Bohr's view emphasized the limits of what can be meaningfully said about nature, focusing instead on observations and probabilities. Both perspectives have influenced modern physics in different ways, shaping how scientists think about measurement, information, and reality. Even today, echoes of their debate continue in discussions about quantum foundations. New experiments, improved technologies, and deeper theoretical insights continue to refine our understanding. Yet the fundamental questions remain remarkably persistent. The Great Debate reminds us that scientific progress is not only about discovering new equations, but also about interpreting what those equations mean. In the case of quantum mechanics, the mathematics is clear and powerful, while the meaning remains subtle and open to exploration. In this space between certainty and interpretation, quantum theory continues to inspire both precision and wonder, standing as one of the most successful yet conceptually challenging achievements in human thought. As quantum mechanics matured into a more complete framework, physicists began to realize that even the idea of empty space needed to be reconsidered. In classical thinking, a vacuum is simply the absence of matter. It is a region where nothing exists. No particles, no energy, and no activity. It is the closest thing imaginable to true emptiness. Quantum physics reveals that this idea of emptiness is not accurate. To describe nature at deeper levels, physicists developed quantum field theory, a framework in which the most fundamental entities are not particles themselves, but fields that fill all of space. Every type of particle corresponds to a field that exists everywhere, even in regions that appear completely empty. For example, electrons are not treated as isolated objects that move through space like tiny beads. Instead, they are understood as excitations of an electron field that permeates the universe. Photons arise from the electromagnetic field. Quarks arise from their own respective fields. In this picture, particles are not the basic building blocks of reality, but rather localized disturbances in underlying fields. This shift in perspective changes the meaning of empty space. Even in the absence of particles, these fields remain present. They are not turned off or removed. Instead, they exist in their lowest possible energy state, known as the vacuum state. However, this vacuum is far from inactive. Due to the uncertainty principle, fields cannot remain perfectly still. Small fluctuations constantly appear and disappear, giving rise to what are known as quantum fluctuations. These fluctuations mean that the vacuum is not truly empty. It is more like a restless background filled with temporary variations in energy. Particles can briefly emerge from these fluctuations and then vanish again, a process that does not violate conservation laws when viewed through the full quantum framework. Although these virtual particles cannot be directly observed in the same way as stable particles, their effects can be measured indirectly. One of the most famous examples is the Casimir effect. When two uncharged metal plates are placed extremely close together in a vacuum, they experience a small attractive force. This force arises from differences in quantum fluctuations between the inside and outside regions, demonstrating that the vacuum itself has physical properties. Another important consequence of quantum fields is that interactions between particles are also described in terms of fields. Forces are not transmitted by direct contact, but through field interactions. The electromagnetic force, for example, is mediated by the electromagnetic field, and in quantum theory, this interaction is described in terms of photons. Similarly, other fundamental forces are associated with their own fields and exchange particles. This field-based picture provides a more unified understanding of the microscopic world. Instead of thinking about particles moving through empty space and occasionally interacting, quantum field theory describes a universe where fields are primary and particles are emergent features of those fields. What we perceive as particles are simply stable, quantized excitations traveling through a continuous underlying structure. The vacuum state itself plays a crucial role in this framework. It is not a passive backdrop, but an active participant in physical processes. It influences particle behavior, contributes to measurable effects, and forms the baseline from which all excitations arise. Even the mass of particles and the strength of certain interactions are related to how fields behave in the vacuum. One of the most striking implications of quantum field theory is that the distinction between something and nothing becomes less clear. In classical physics, nothingness means complete absence. In quantum physics, the vacuum is a structured state with its own properties and dynamics. It is empty of particles, but not empty of physics. This perspective also connects deeply with cosmology. In the early universe, quantum fluctuations in fields are believed to have played a role in the formation of galaxies and large-scale structure. Tiny variations in the vacuum state may have been amplified over cosmic time, eventually shaping the distribution of matter we observe today. Quantum fields also help explain why particles behave in consistent and predictable ways. The properties of particles, such as mass, charge, and spin, are determined by the structure of the fields they arise from. These fields obey precise mathematical equations that govern how excitations can form and interact. Although quantum field theory is highly successful, it remains conceptually challenging. The idea that empty space is filled with invisible fields and constant fluctuations contradicts everyday intuition. Yet experiments consistently support this framework with extraordinary precision. In this view, the universe is not a collection of isolated objects moving through empty space. Instead, it is a dynamic system of interacting fields, with particles emerging as temporary, localized expressions of deeper underlying structures. Even the vacuum, once thought to be nothing at all, becomes a rich and active component of reality. It is a reminder that in the quantum world, emptiness is never truly empty, and silence is never completely still. Once quantum field theory revealed that empty space is filled with active fields, physicists began exploring the strange consequences of this restless vacuum. One of the most intriguing ideas that emerged from this framework is the concept of virtual particles, temporary excitations that appear and disappear within quantum fluctuations. In everyday thinking, particles are imagined as stable objects. An electron, for example, seems like a tiny entity that exists continuously and can be tracked as it moves through space. In quantum field theory, however, particles are better understood as excitations of underlying fields. These excitations can sometimes be long-lived and stable, but they can also appear briefly as transient disturbances of the vacuum. Virtual particles are not particles in the same sense as electrons, or photons that can be directly detected. Instead, they are temporary mathematical features that arise in the calculations of quantum interactions. They represent intermediate states that help describe how fields influence each other over time. Although virtual particles cannot be observed directly, their effects are real and measurable. They contribute to forces between particles, modify energy levels in atoms, and influence the behavior of fields even in empty space. In this sense, they are not imaginary in a casual sense, but rather part of the deeper structure of quantum theory. The origin of virtual particles lies in the uncertainty principle. Because energy and time are linked by quantum uncertainty, small violations of energy conservation can occur over extremely short time intervals, as long as they balance out over longer scales. This allows temporary fluctuations in energy to manifest as particle-like excitations that quickly vanish again. These short-lived events are what give rise to the idea of virtual particles. One of the most important roles of virtual particles is in mediating forces. In quantum field theory, forces are not transmitted by direct contact, but through exchanges of field excitations. For example, the electromagnetic force between charged particles can be described as the exchange of virtual photons. These photons are not directly observed, but their exchange produces the familiar attraction and repulsion between charges. Similarly, other fundamental forces are described through the exchange of different types of virtual particles associated with their respective fields. These exchanges create the effects that we interpret as forces acting at a distance. In this framework, what appears to be a simple interaction between two objects is actually a complex process involving the underlying quantum fields. Virtual particles also play a role in subtle corrections to physical quantities. One famous example is the Lamb shift, a small difference in energy levels within the hydrogen atom that cannot be explained by simpler quantum models. This shift arises because virtual particles in the vacuum slightly modify the behavior of the electron field. Precise measurements of this effect provided strong confirmation of quantum electrodynamics, one of the most accurate theories in physics. Another striking consequence of virtual particle activity is the polarization of the vacuum. In the presence of strong electric fields, the vacuum behaves as though it becomes slightly polarized due to the influence of virtual particle pairs. This effect changes how charges interact at very small distances and contributes to extremely precise corrections in theoretical predictions. In extreme conditions, such as near very strong gravitational fields or in high-energy collisions, virtual particles can have even more dramatic effects. They may influence radiation processes or contribute to phenomena like Hawking radiation near black holes, where quantum effects at the edge of intense gravity lead to the slow emission of particles from what would otherwise appear to be empty space. Despite their name, virtual particles should not be thought of as little objects popping in and out of existence like physical beads. Instead, they are part of the mathematical machinery that allows quantum field theory to describe interactions consistently and accurately. They are useful representations of the underlying fluctuations and correlations in quantum fields. One of the most important lessons from virtual particles is that the vacuum is not passive. It is a dynamic environment where fluctuations constantly occur, influencing the behavior of all physical systems, even when no real particles are present. The structure of the vacuum continues to shape physical reality. This leads to a deeper realization. What we perceive as empty space is actually filled with structure, activity, and subtle interactions. The difference between presence and absence becomes less absolute at the quantum level. Instead, reality is defined by fields and their fluctuations, whether or not stable particles are present. Quantum fluctuations and virtual particles therefore extend the idea of quantum mechanics into the very fabric of space itself. They show that even in the quietest regions of the universe, something is always happening beneath the surface. The vacuum is not silent emptiness, but a continuously active background that influences everything that exists. In this way, quantum field theory transforms our understanding of nothingness. Empty space is no longer empty. It is a living, fluctuating medium from which particles emerge, interact, and disappear, all governed by the deep and elegant rules of quantum physics. As quantum field theory deepened our understanding of the vacuum, physicists began to notice something even more profound. Not only do fields fill space and produce particles as excitations, but the forces that govern interactions between matter also emerge from these fields in a very specific way. Instead of thinking about forces as invisible pushes or pulls acting across distance, quantum physics describes them as interactions mediated by exchange, particles associated with underlying fields. In classical physics, forces were straightforward. Gravity pulled objects together. Electricity and magnetism caused attraction or repulsion between charges. These influences were described as fields in space. But the idea of a force still carried the intuition of something acting directly between objects. Quantum mechanics replaced this picture with something more structured and more subtle. Each fundamental force corresponds to its own quantum field, and interactions between particles occur through the exchange of field excitations. These excitations are what we call force-carrying particles. They are not separate from the field, but rather expressions of it in quantized form. The electromagnetic force is mediated by photons. In this framework, charged particles interact by exchanging photons through the electromagnetic field. This exchange produces the familiar attraction between opposite charges and repulsion between like charges. What appears in classical physics as a smooth force is, in quantum theory, the result of countless microscopic exchanges governed by probability amplitudes. The strong nuclear force, which binds quarks together inside protons and neutrons, is carried by gluons. Gluons themselves interact strongly with each other, creating an extremely complex and powerful field structure. This interaction is responsible for the confinement of quarks, ensuring they are never observed in isolation under normal conditions. The strength of this force is so great that it dominates the behavior of matter at subatomic scales. The weak nuclear force is mediated by massive particles known as W and Z, bosons. Unlike photons, which are massless and allow electromagnetic effects to extend over long distances, these particles are heavy and short-lived. As a result, the weak force operates only over extremely small distances. It plays a crucial role in processes such as radioactive decay and certain types of nuclear reactions that occur inside stars. Gravity, the most familiar force in everyday life, remains more challenging to fully integrate into the quantum framework. In many theoretical approaches, gravity is associated with a hypothetical particle called the graviton, which would mediate gravitational interactions in a way similar to other forces. However, a complete and experimentally verified quantum theory of gravity has not yet been established. Despite this, quantum field concepts still provide important insights into how gravity might behave at very small scales. One of the most important insights of this framework is that forces are not fundamental entities acting independently. Instead, they arise from the structure and symmetries of quantum fields. The rules governing how fields interact determine the types of force-carrying particles that exist and how they behave. In this sense, the diversity of forces in nature reflects deeper mathematical structures embedded in the quantum description of reality. Another striking feature of these interactions is that they are inherently probabilistic. When two particles interact, there is not a single predetermined outcome. Instead, there are multiple possible interaction paths, each contributing to the overall probability of the final result. These paths are described mathematically using amplitudes, which combine in ways that can reinforce or cancel each other, producing the observed physical behavior. This probabilistic nature allows quantum field theory to make extremely precise predictions. For example, the interactions involving photons and electrons have been tested to extraordinary accuracy, making quantum electrodynamics one of the most successful theories in all of science. Its predictions match experimental results to many decimal places, demonstrating that even though the underlying processes are probabilistic, the overall structure is remarkably consistent. The concept of force carriers also helps unify our understanding of matter and interactions. Matter particles, such as electrons and quarks, are excitations of their respective fields. Force carriers are excitations of other fields that mediate interactions between matter fields. In this way, the universe can be seen as a vast network of interconnected fields, constantly interacting through quantized exchanges. Even the vacuum plays a role in these interactions. Virtual particles and fluctuations in fields contribute to the way forces behave at small scales, subtly modifying interaction strengths and energy levels. This means that empty space is not just a passive background, but an active participant in the dynamics of forces. As physicists continue to explore these ideas, the goal is to understand whether all forces can be described within a single unified framework. Many theories suggest that at extremely high energies, the distinctions between different forces may begin to merge, hinting at a deeper underlying unity in the structure of reality. For now, quantum field theory provides a remarkably successful description of 3 of the 4 known fundamental forces, and a strong foundation for understanding how interactions shape the behavior of matter. It reveals a universe where forces are not invisible pushes acting across empty space, but expressions of underlying fields exchanging quantized signals in a continuous and dynamic structure. In this view, reality is not built from isolated objects connected by forces, but from fields that constantly interact, overlap, and transform one another, producing the rich and complex behavior observed throughout the cosmos. As quantum electrodynamics demonstrated how accurately nature could be described through quantum fields, physicists began extending the same framework to all known fundamental interactions. Over time, this effort led to the construction of one of the most successful scientific theories ever developed, known as the Standard Model of particle physics. The Standard Model is not a single equation, but a comprehensive framework that describes the fundamental particles and forces, except gravity, using quantum field theory. It organizes the known constituents of matter and their interactions into a structured and remarkably consistent system. At the most basic level, the Standard Model divides particles into 2 main categories. The first category consists of matter particles, known as fermions. These include electrons, neutrinos, and quarks. Fermions are the building blocks of atoms and everything composed of them. They obey the Pauli exclusion principle, which prevents identical fermions from occupying the same quantum state. This property is essential for the stability and diversity of matter. The second category consists of force-carrying particles, known as bosons. These include photons, gluons, and the W and Z bosons. Bosons are responsible for mediating the interactions between matter particles. Unlike fermions, bosons can occupy the same quantum state, which allows them to form coherent fields such as light beams. The fermions themselves are organized into 3 generations. The first generation contains the particles that make up ordinary matter, such as electrons and the up and down quarks that form protons and neutrons. The second and third generations consist of heavier, less stable particles that appear only in high-energy environments, such as cosmic rays or particle accelerators. Although these heavier particles are not commonly found in everyday matter, they play an important role in understanding the full structure of particle physics. Quarks are especially important because they combine to form protons and neutrons, which in turn form atomic nuclei. Quarks are never found in isolation under normal conditions due to the strong nuclear force, a phenomenon known as confinement. Instead, They are permanently bound together inside composite particles called hadrons. This behavior is a direct consequence of quantum chromodynamics, the quantum field theory describing the strong interaction. The strong force is carried by gluons, which themselves interact with one another. This self-interaction gives the strong force its unique properties, including its extreme strength at small distances and its weakening behavior at larger scales, known as asymptotic freedom. This complex structure is essential for the stability of atomic nuclei and the existence of matter as we know it. The electroweak interaction unifies the electromagnetic force and the weak nuclear force into a single theoretical framework. At low energies, these forces appear distinct, with electromagnetism governing light and chemical interactions, and the weak force governing radioactive decay. However, at very high energies, such as those present in the early universe, these forces merge into a unified interaction. The W and Z bosons are responsible for mediating the weak force, while the photon mediates electromagnetism. One of the most significant achievements of the Standard Model was the prediction and later discovery of the Higgs boson. The Higgs field is a pervasive field that fills all of space, and particles acquire mass through their interaction with it. The discovery of the Higgs boson confirmed this mechanism and completed a major part of the Standard Model framework. Despite its success, the Standard Model is not considered a final theory. It does not include gravity, nor does it explain dark matter or dark energy, which appear to make up most of the universe. It also leaves several fundamental parameters unexplained, such as the exact masses of particles and the strengths of certain interactions. These unknowns suggest that a deeper underlying theory may still exist. Nevertheless, the Standard Model remains one of the most accurate scientific frameworks ever created. Its predictions have been tested repeatedly in particle accelerators and high-energy experiments, with results that consistently match theoretical expectations to extraordinary precision. What makes the Standard Model especially remarkable is that it describes an enormous range of phenomena using a relatively small set of particles and interactions. From the structure of atoms to the behavior of high-energy cosmic events, it provides a unified language for understanding the microscopic world. In this framework, the universe is composed not of solid building blocks in the classical sense, but of interacting quantum fields whose excitations appear as particles. Matter and force are no longer fundamentally separate categories, but different expressions of the same underlying quantum structure. The Standard Model, therefore, represents a major step in humanity's understanding of reality. It reveals a world where complexity emerges from a small number of fundamental principles, and where the behavior of everything from atoms to high-energy particles can be traced back to the interactions of quantum fields. Even so, it remains part of a larger, unfinished story. Beneath its success lies the continuing search for a more complete theory that includes gravity and explains the deeper origins of the constants and structures we observe. The Standard Model is not the end of the journey, but a powerful and precise map of a vast and still partially unexplored quantum landscape. As quantum mechanics continued to reshape our understanding of matter and fields, a new idea began to emerge that focused not only on what the universe is made of, but on how information itself behaves at the quantum level. This line of thought eventually led to the concept of quantum computing, a radically different way of processing information that relies directly on the principles of superposition, entanglement, and quantum evolution. In classical computing, information is stored in bits. Each bit can take one of two values, typically represented as 0 or 1. All digital technology, from simple calculators to modern supercomputers, is built on long sequences of these binary states. Computation occurs through logical operations that manipulate bits in a deterministic or probabilistic way, but always within a clearly defined framework of definite states. Quantum computers replace classical bits with quantum bits, known as qubits. Unlike classical bits, A qubit can exist in a superposition of both 0 and 1 at the same time, described by a wave function that assigns probabilities to each outcome. This means that a quantum system with multiple qubits can represent a vast number of possible states simultaneously. As more qubits are added, the number of possible configurations grows exponentially. A system of just a few dozen qubits can represent more states than there are atoms in a large object. This does not mean that all these states are directly accessible at once in a classical sense. Instead, quantum computation works by carefully manipulating interference patterns between these possibilities. The key idea behind quantum computing is that computation is not just about storing information, but about guiding the evolution of probability amplitudes. Quantum algorithms are designed so that unwanted computational paths cancel each other through destructive interference, while correct answers are reinforced through constructive interference. The final measurement then reveals the result with high probability. Entanglement plays a central role in this process. Qubits can become linked in such a way that the state of one depends on the state of another, even across large separations within the system. This interconnected structure allows quantum computers to process information in ways that are fundamentally different from classical machines. One of the most famous examples of quantum algorithms is Shor's algorithm, which can factor large numbers exponentially faster than known classical methods. This has significant implications for cryptography, as many encryption systems rely on the difficulty of factoring large integers. Another important algorithm is Grover's search algorithm, which provides a quadratic speedup for searching unsorted databases. Despite these theoretical advantages, building practical quantum computers is extremely challenging. Quantum systems are highly sensitive to their environment, and even small interactions with surrounding particles can destroy delicate superpositions through a process known as decoherence. Maintaining stability requires extremely low temperatures, precise isolation, and advanced error correction techniques. Quantum error correction itself is a remarkable development. It allows fragile quantum information to be protected by encoding it across multiple entangled qubits. This makes it possible, in principle, to perform reliable computation even in the presence of noise, although the technical requirements are demanding. Beyond computation, quantum information theory has also reshaped how physicists think about reality. It suggests that information is not just a tool for describing physical systems, but may be a fundamental component of physical law itself. Concepts such as entropy, information flow, and entanglement entropy have become central to modern theoretical physics, especially in areas like black hole physics and quantum gravity. In this view, the universe can be thought of as a vast quantum information processor, where physical processes correspond to transformations of information encoded in quantum states. Matter, energy, and even space-time itself may emerge from deeper informational structures governed by quantum rules. Quantum computing also provides a practical window into these ideas. By building and manipulating small quantum systems in laboratories, scientists can directly observe phenomena that reflect the underlying structure of quantum mechanics. These experiments are not only technological milestones, but also tests of the fundamental principles that describe reality. Although large-scale quantum computers are still under development, their conceptual foundation already represents a major shift in how computation and information are understood. They show that the strange features of quantum mechanics are not just theoretical curiosities, but powerful tools that can be harnessed to process information in entirely new ways. In this way, quantum computing connects abstract quantum principles to practical applications, while also deepening our understanding of the relationship between physics and information. It reveals a universe where computation is not separate from physical law, but embedded within it, and where information itself follows the same quantum rules that govern matter and energy. For a long time, Quantum mechanics was thought to belong only to the world of atoms, electrons, and high-precision laboratory experiments. Living systems, warm and noisy as they are, seemed far too large and chaotic for delicate quantum effects to survive. Biology was traditionally explained through chemistry and classical physics, where molecules interact in predictable ways and thermal motion dominates behavior. Yet over time, scientists began discovering hints that quantum mechanics might play a subtle role even in biological processes. At first, this idea was controversial. The warm and wet environment of living cells causes constant interaction with surrounding molecules. These interactions typically destroy quantum superpositions very quickly through decoherence. Because of this, it was assumed that quantum effects would be washed out long before they could influence anything meaningful in biology. However, certain biological processes appeared to operate with efficiencies that were difficult to explain using classical models alone. This led researchers to investigate whether quantum phenomena might be involved in specific microscopic mechanisms inside living organisms. One of the most studied examples is photosynthesis. In plants, algae, and certain bacteria, light energy is captured and transferred with remarkable efficiency. When a photon is absorbed, its energy must travel through a complex network of molecules to reach a reaction center, where it is converted into chemical energy. Classical models suggested that this energy transfer should involve a kind of random hopping process, which would naturally lead to energy loss. Experimental evidence, however, has shown signatures consistent with wave-like energy transfer. In some cases, the excitation appears to explore multiple pathways simultaneously, similar to quantum superposition, allowing it to effectively sample different routes at once and select the most efficient path. This quantum coherence may help explain why photosynthesis operates with such high efficiency under certain conditions. Another fascinating example is found in the navigation abilities of some birds. Certain species are believed to use the Earth's magnetic field to orient themselves during long migrations. One proposed explanation involves quantum effects in light-sensitive proteins within their eyes. These proteins may form radical pairs whose spin states are influenced by weak magnetic fields, allowing the birds to detect subtle variations in the planet's magnetic environment. Although the full mechanism is still under investigation, the role of quantum spin dynamics is a leading hypothesis. Enzymes, the biological catalysts that speed up chemical reactions in living cells, may also exhibit quantum behavior. Some reactions involve particles crossing energy barriers that are too high to be explained by classical thermal motion alone. Quantum tunneling provides a possible explanation, allowing particles such as protons to pass through barriers and accelerate reactions that are essential for life. Even DNA mutations have been discussed in the context of quantum mechanics. In some theoretical models, quantum tunneling could allow protons within DNA base pairs to shift positions, potentially leading to rare copying errors during replication. While the overall role of quantum effects in genetics is still being studied, it highlights how deeply microscopic quantum processes might influence biological outcomes. Despite these intriguing examples, it is important to maintain perspective. Most biological processes are still well described by classical chemistry and molecular biology. Quantum biology does not replace these fields. Instead, it explores specific cases where quantum effects may play a measurable or supportive role in enhancing efficiency or enabling otherwise unlikely processes. What makes quantum biology particularly interesting is not that life somehow escapes classical physics, but that it may sometimes exploit quantum physics in subtle and highly specialized ways. Evolution operates through natural selection, and even small advantages in efficiency or sensitivity could, over long time scales, lead to biological systems that take advantage of quantum effects when beneficial. This raises deeper questions about the relationship between life and quantum mechanics. If quantum processes contribute to biological function, then living systems are not just macroscopic classical objects, but complex quantum systems operating at the edge of decoherence. They exist in a regime where classical and quantum descriptions overlap. At the same time, life demonstrates how robust macroscopic order can emerge despite underlying quantum uncertainty. Cells maintain structure, organisms develop predictable forms, and biological processes remain stable, even though the underlying components obey probabilistic quantum laws. This balance between quantum unpredictability and biological order is one of the most fascinating aspects of nature. Quantum biology is still a developing field. Many of its ideas remain under active research, and some proposed mechanisms are not yet fully confirmed. However, it has already opened new perspectives on how deeply quantum mechanics may be woven into the fabric of life. In this view, living systems are not isolated from quantum reality. Instead, they may be quietly shaped by it at the smallest scales, where particles, waves, and probabilities influence processes that ultimately contribute to the emergence and continuation of life itself. As quantum mechanics successfully described the microscopic world, and general relativity explained gravity on cosmic scales, physics found itself with two extraordinarily successful theories that do not naturally fit together. Each theory works with extreme precision in its own domain. Yet when both are applied at the same time, especially in extreme environments like black holes or the early universe, inconsistencies begin to appear. This tension has led to one of the most important open problems in modern physics, the search for a theory of quantum gravity. General relativity describes gravity not as a force in the traditional sense, but as the curvature of space and time caused by mass and energy. Planets orbit stars not because they are pulled by an invisible force, but because they follow the natural geometry of curved space-time. This geometric picture has been confirmed in countless experiments, from the bending of light around massive objects to the precise behavior of GPS satellites. Quantum mechanics, on the other hand, describes all other fundamental interactions using probabilistic fields and particles. It introduces uncertainty, superposition, and entanglement as essential features of reality. In quantum theory, even empty space is active, and physical quantities do not always have definite values until measured. The challenge arises when gravity is examined at very small scales, where quantum effects cannot be ignored. Near the center of a black hole or during the earliest moments after the Big Bang, matter is compressed into extremely dense states where both quantum mechanics and gravity must operate simultaneously. In these regimes, the smooth geometry of space-time described by general relativity is expected to fluctuate, but a complete description of these fluctuations is not yet fully understood. One approach to quantum gravity is to treat gravity itself as a quantum field, similar to other forces. In this framework, the gravitational interaction would be mediated by hypothetical particles called gravitons. These particles would represent quantized excitations of the gravitational field, carrying the force of gravity in discrete packets. However, constructing a fully consistent quantum field theory of gravity has proven extremely difficult due to mathematical complications that arise at very high energies. Another major approach is string theory, which proposes that the fundamental building blocks of the universe are not point-like particles, but tiny vibrating strings. Different vibrational modes of these strings correspond to different particles, including those that would carry gravitational interactions. In this framework, gravity emerges naturally from the geometry of string vibrations, and quantum consistency requires additional spatial dimensions. Beyond the familiar three, a different perspective comes from loop quantum gravity, which attempts to quantize spacetime itself rather than treating it as a continuous background. In this view, space is not infinitely divisible, but composed of discrete units connected in a network-like structure. These quantum loops define the smallest possible structures of geometry, suggesting that spacetime has an underlying granular nature at the Planck scale. Despite these different approaches, no single theory has yet been experimentally confirmed. The energies required to directly test quantum gravity effects are far beyond current technological capabilities. However, indirect evidence and theoretical consistency continue to guide research in this area. One of the most promising testing grounds for quantum gravity is black hole physics. Black holes represent regions where gravity is so strong that classical descriptions of spacetime break down. The event horizon, the boundary beyond which nothing can escape, raises deep questions about information, entropy, and the fate of matter that falls inside. Quantum mechanics suggests that information cannot be destroyed, while classical black hole theories seem to imply that information could be lost forever. This conflict led to the famous black hole information paradox. Over time, developments such as Hawking radiation and holographic principles have suggested that information may be preserved in subtle quantum ways, possibly encoded on the surface of the black hole, or released through quantum processes over extremely long timescales. The search for quantum gravity is therefore not just about unifying equations, but about understanding the deepest structure of reality itself. It asks whether spacetime is continuous or discrete, whether geometry is fundamental or emergent, and how quantum information behaves under extreme gravitational conditions. Even though a final theory remains elusive, progress in this area has already reshaped modern physics. It has revealed unexpected connections between gravity, thermodynamics, and information theory, suggesting that these concepts may all be different expressions of a deeper underlying framework. In this sense, quantum gravity represents the frontier where the two great pillars of modern physics meet. It is a region of ideas where space, time, matter, and information begin to merge into a single, still incomplete picture of the universe. Black holes represent one of the most extreme predictions of general relativity, regions where matter collapses under its own gravity until spacetime itself becomes intensely curved. From a classical perspective, a black hole is simple in definition but extreme in consequence. Once something crosses the event horizon, the boundary surrounding the black hole, it cannot return. Not even light can escape. This idea already stretches intuition, but quantum mechanics adds an even deeper layer of mystery. In quantum theory, physical systems are described by wave functions that evolve smoothly and preserve information. The evolution is governed by precise mathematical rules that, in principle, do not allow information to disappear. Every quantum state can be traced forward and backward in time through unitary evolution. This creates a tension when combined with the classical picture of black holes. If something falls into a black hole, classical reasoning suggests it is lost forever to the outside universe. Yet quantum mechanics insists that information about the system must be preserved in some form. This conflict leads to one of the most famous problems in theoretical physics, the black hole information paradox. Stephen Hawking made a groundbreaking discovery that deepened this puzzle. He showed that black holes are not completely black. Instead, they emit a faint form of radiation due to quantum effects near the event horizon. This is now known as Hawking radiation. It arises because quantum fluctuations in the vacuum can produce particle-like excitations near the boundary of the black hole, with some particles escaping while others fall in. Over extremely long timescales, this radiation causes black holes to slowly lose mass and eventually evaporate. This leads to a troubling question. If a black hole completely evaporates, what happens to the information about everything that fell into it? If the radiation is purely thermal, containing no detailed information about the original matter, then information appears to be destroyed. This would violate a core principle of quantum mechanics. If, on the other hand, the information is somehow encoded in the radiation in subtle correlations, then the evaporation process must be far more complex than initially thought. Modern developments in theoretical physics strongly suggest that information is not lost. Instead, it may be encoded in highly subtle quantum correlations within Hawking radiation, preserved in ways that are extremely difficult to decode. This resolution preserves the consistency of quantum mechanics, but requires a deep rethinking of how information is stored in spacetime. Another important concept related to black holes is entropy. Black hole entropy is proportional not to the volume of the black hole, but to the area of its event horizon. This surprising relationship suggests that the information content of a region of space may be encoded on its boundary rather than in its interior. This idea led to the development of the holographic principle, which proposes that the full description of a volume of space can be represented by information stored on its surface. If this principle is correct in a fundamental sense, it would radically change our understanding of reality. Space itself could emerge from more basic informational structures defined on lower dimensional boundaries. In such a view, what we perceive as three-dimensional space might be a projection of deeper quantum information encoded elsewhere. Black holes also highlight the interplay between gravity, quantum mechanics, and thermodynamics. The laws governing black hole behavior resemble the laws of heat and entropy in surprising ways. Temperature, entropy, and energy all appear in black hole physics, suggesting that spacetime itself may have thermodynamic properties. This connection has led to the idea that gravity might not be a fundamental force in the traditional sense, but an emergent phenomenon arising from underlying statistical or informational processes. In this perspective, spacetime curvature could emerge from the collective behavior of microscopic degrees of freedom, much like temperature emerges from molecular motion. Despite decades of research, many questions remain unanswered. The precise mechanism by which information escapes from evaporating black holes is still under active investigation. The full nature of quantum spacetime and how it behaves at the Planck scale remains one of the deepest mysteries in physics. What black holes ultimately reveal is that the boundary between known physics and unknown physics is not a sharp line, but a region of increasing subtlety. At these extreme limits, classical concepts of space, time, and information begin to blur, and quantum effects become inseparable from gravitational behavior. In this region, reality appears to behave less like a collection of objects in space, and more like a dynamic interplay of geometry, information, and quantum correlations. Black holes, therefore, serve not only as cosmic objects, but as gateways to deeper questions about the fundamental structure of the universe itself. At the end of this long journey through quantum mechanics, the picture that emerges is not one of simple particles moving through empty space, but of a universe built from layers of structure that become more abstract and more fundamental as we go deeper. What begins as matter in motion gradually transforms into waves, probabilities, fields, and finally into relationships between information and geometry. In the everyday world, reality feels solid and stable. Objects have clear shapes, positions, and behaviors. A table remains a table whether it is observed or not. A planet follows a predictable orbit. This macroscopic stability is real, but it is not fundamental. It is the emergent result of vast numbers of quantum interactions averaging out into classical behavior. At the quantum level, the situation is very different. Particles do not possess fixed properties in the way classical objects do. Instead, they exist in superpositions of possible states, described by wave functions that evolve smoothly and deterministically until a measurement occurs. The outcomes of those measurements are probabilistic, governed by precise mathematical rules rather than deterministic certainty. Even more deeply, particles themselves are not truly fundamental. In quantum field theory, what we call particles are excitations of underlying fields that exist everywhere in space. These fields interact, fluctuate, and combine, producing the phenomena we interpret as matter and energy. The vacuum is not empty, but filled with structure and activity at all times. Interactions between these excitations are mediated by exchange processes that we interpret as forces. Photons, gluons, and other force carriers are not separate from reality, but expressions of how fields communicate. What we perceive as attraction, repulsion, or decay is the visible outcome of deeper quantum interactions unfolding continuously. As the scale of description shifts further, even space-time itself begins to lose its classical meaning. In extreme conditions such as black holes or the early universe, space and time appear to be influenced by quantum information and may emerge from more fundamental underlying structures. Entanglement, once thought of as a strange connection between particles, now appears as a possible building block of space-time geometry itself. Across all of these layers, a consistent pattern appears. The universe is not built from isolated objects, but from relationships. Particles are defined by fields. Fields are defined by symmetries. Symmetries are expressed through mathematical laws, and those laws govern how information evolves across the entire system. One of the most profound aspects of quantum mechanics is that it does not describe reality as something fully definite and predetermined. Instead, it describes a landscape of possibilities, where atoms are shaped by probabilities, interference, and constraints imposed by underlying structure. Yet despite this probabilistic foundation, the large-scale world remains remarkably stable and predictable. This stability emerges because quantum effects tend to average out at large scales. Decoherence, interactions with the environment, and the sheer number of particles involved ensure that macroscopic objects behave in ways that resemble classical physics. The quantum world does not disappear at large scales, but it becomes hidden beneath layers of complexity. At the same time, quantum effects remain essential. Without them, atoms would not exist, chemistry would not function, and life itself would be impossible. The stability of matter, the structure of molecules, and the behavior of light all depend on quantum rules operating at the smallest scales. This dual nature of reality, where quantum unpredictability gives rise to classical stability, is one of the central themes of modern physics. It suggests that the universe is neither purely deterministic nor purely random, but something more subtle. It is a system governed by precise mathematical laws that produce probabilistic outcomes, which in turn create stable structures when viewed at larger scales. Even our understanding of information has changed through quantum theory. Information is no longer just a passive record of events, but an active physical quantity that can be stored, transformed, and entangled. In some modern perspectives, information may even be more fundamental than matter or energy, with physical reality emerging from deeper informational processes. What remains consistent throughout all these layers is the presence of mathematical structure. Whether describing particles, fields, space-time, or information, quantum mechanics reveals a universe governed by precise relationships that can be expressed in elegant mathematical form. These relationships do not depend on human observation to exist, but they define what can be observed. In the end, quantum mechanics does not replace reality with abstraction. Instead, it reveals that reality itself is structured in a way that is far more subtle and interconnected than everyday intuition suggests. Beneath the surface of solid objects and familiar experiences lies a dynamic quantum framework where waves, fields, probabilities, and information continuously shape everything that exists. The universe, as seen through quantum mechanics, is not a static collection of things. It is an evolving network of possibilities, constrained by deep mathematical rules, where even emptiness is active and even separation is connected. And within this hidden order, the familiar world quietly emerges, stable enough to live in, yet always rooted in a far more intricate quantum foundation.